And hello again. This is the final day of the hottest conference. We made it. And so with no further delay, I'm going to introduce our speaker today, Eric Finster, who will speak about weak structures from strict ones.
Okay, well, thank you very much to the organizers for organizing a really great conference. I've been really enjoying the talks. The work I'm going to speak about today is joint work with Mathieu Sozo and Antoine Aliou. And right, so the problem is the the perennial one that I've thought about for a long time, and it's the problem of understanding how to define higher structures in homotopy type theory. And so one of the original goals, or at least for someone like me coming from topology, is to imagine homotopy type theory as a foundation for higher mathematics, for proof relevant mathematics. And the thing that we've really come to understood is how much that's related to classical homotopy theory, which is a really fantastic and interesting connection. But one of the main problems, though, that's still sort of a stumbling block for this vision of what hot can be, is that we can't seem to define interesting algebraic structures on types unless we assume they're truncated. So we can't seem to write down these infinitely coherent objects and do what is higher algebra inside of type theory. And so this has been a thorn in our side for a long time, and I've thought about this problem a lot. Today I'm going to present sort of a new approach to this problem, or a variation on an approach to this problem. So just to survey the two sort of main outlying approaches to talking about higher structures in hot, or variations of hot, are the first, I would say, is the synthetic approach. So there are a number, we've seen even examples in this conference. You can extend hot with new axioms, new principles, so that the objects take on some additional character. They could take on the character of some algebraic structure, some topological structure, something else. But the main idea of the sort of synthetic approaches to higher structures is to sort of play the same game that hot does for infinity groupoids and make the basic objects of some new theory be some new type of structure. So I think most attempts at coming up with a directed approach to type theory sort of fall under this umbrella. But then there are also the approaches for other synthetic things, like synthetic spectra that we saw this week, and you have like you have the synthetic infinity categories in the topos of simplicial spaces that Mike and Emily have worked on, right. And so this is a really great thing to do, a really useful thing to do. But it has sort of one major drawback, is that it's synthetic. I mean, I know it's meant to be. In many cases, that's a good thing to separate the axioms you're using about a structure from something else, but that means it leaves out the possibility of showing that you have instances of those axioms, or at least not in any obvious way, I think, in many of these approaches. And on the other hand, we know that there are many examples of higher structures from mathematics. So, so the synthetic approach doesn't sort of get us everything we want when we think about a sort of foundation for proof-relevant mathematics. And the second approach is the two-level approach, which has been proposed by a number of authors, where we sort of have a two-level theory where we have some meta theory with some extra strictness, in which we can sort of discuss coherence problems in the same way, roughly, that they're discussed in mathematics, which is that we give ourselves some strict set truncated types with a special equality which has some more properties, and we use this to make definitions about higher structures. And this is also a totally useful tool, especially if you're doing meta theory and things like this. Is a totally natural and normal thing to do. But for someone coming from traditional mathematics, where there is already a very strong theory of presentation, the theory of model categories, somehow the dream of homotopy type theory is to be working with invariant objects all the time. And so there's maybe some, at least for me, we're giving up something by reintroducing set level structures. We're sort of, so I'm interested in seeing if there can be a third approach, and that's what I'm gonna propose today, which is somewhat similar. I mean, in the sense that I'm going to be adding some new principles and some new computational principles to type theory. And that's going to come in the form of a universe of strict structures, which I'll explain more about. And everything that I'm talking about today, you can find on GitHub. So all the theorems and the definitions and whatnot have all been implemented. And this is the point where I have to apologize a little bit for members of the audience who are coming from a more mathematical or abstract background, because I think this is going to be a fairly technical type theoretic talk. But somehow this coherence problem that we face is a very technical type theoretic issue. So I can't somehow really talk about it in a very general categorical framework. I'm going to have to sort of go into the details. And practically speaking, that means I'm going to be showing a lot of code. Also because I haven't had time to transform what I've been, this presentation here, in sort of a more traditional mathematical one. So I'll try to go slow, and I'll try to bring along some intuition as much as I can, but there is going to be some hardcore type theory here. So, hope that doesn't scare anyone off. Anyway, okay, so let's get started. So the basic idea is that we're going to introduce a new universe. And the notion of a universe in type theory is really a trick of the trade kind of thing. When we want to introduce a collection of types with some property or some distinguished collection of types, we sometimes make what people call a universe, which is we make a bunch of a type with some constructors on it that represent codes for the objects we're thinking about, and then we decode them into their semantic form. So, and you can think of the universe of type theory itself as something like this. When we write pi's and sigmas and so on, we're writing syntactic entities which we then provide with semantic meaning via their computation rules or by interpreting them in some actual semantics. So here, I'm going to introduce a new universe, and what that looks like in Agda, which is the language I've been implementing this in, is just a set. So our set is our universe is called M here, and it's an abstract set, and the inhabitants of M are going to be monads, which is why it's called M. And in particular, they're going to be a particular kind of monad. They're going to be Cartesian polynomial monads, and what that means is that every element of M comes equipped with a bunch of structure. And normally, if you just look at the first two lines here, a typical universe in type theory would be a set together with a function that's usually called L, which takes an element of the universe and gets you back a set, which is like the set corresponding to that element of the universe. Here, we have every monad has an underlying set, but it has a bunch of more sets. It has a bunch of families associated to it. And these families are exactly the presentation, the internalized presentation of what people call a polynomial or an indexed container, or yeah, and these are these combinatorial objects, which in some sense represent definitions of inductive or co-inductive types. And this.
Sorry, can I ask a quick question?
Yeah.
By set, you mean Agda sets, or
yeah?
So sets?
Yeah, no, I'm sorry. I just I didn't mask the Agda by saying type, but in Agda, for historical reasons, types are called sets, and so there's no truncation assumption here. Sorry. Yeah. Anyway, so this is what that looks like. A monad is a collection of indices, which are going to play the role of like colors, for example, if you're more familiar with that terminology from operads. I'll call them indices today. A set of constructors, so every index has a set of constructors. Every constructor has a set of positions, which are like its arity, and every input position has a type. I hope this is probably familiar to a lot of people. Here's just a quick drawing. It's useful to think of the elements of our universe consists of monads, and it's useful to think of them as having elements. And their elements are the constructors, which are sort of privileged here. Each constructor has an output, which is actually noted in its type. So constructors are actually fibered over their output type. And then it has a set of input positions, which are just the formal positions. So think of the position set as being the set of inputs. And then there's a typing function, which assigns to each of those inputs an index. So if here in this picture, there are 4 indices running around. C is a constructor with an input arity of 3, and I've written out the typing function. So I hope this is a useful thing to have in mind, that the elements of a monad are sort of elements with some extra decorations somehow. And if you're familiar with the more categorical presentation of polynomials in terms of 3 maps in a locally Cartesian closed category, you get those sets and those 3 maps by just taking the dependent sum of over all these things, and this is what it looks like. So the set of constructors here, you just sum all the constructors over the indices, you sum the positions, and then you have the typing function going this way. So that's the translation. I'm going to be working in type theory, so everything's going to be very long and elaborate, but this does correspond to the traditional notion. Okay, so every element in our universe decodes to this much structure, but more. So now I'm going to add I'm now going to add algebraic structure to each of these things. So in addition, if I have a monad, it has a unit function which takes an index and gives a constructor, and it has a multiplication function, which looks like this. I'll try to read it out. So if given a monad and given an index and a constructor of that index, and given a function assigning to every position a constructor of the appropriate type, I get a new constructor. So you can picture this as saying that for every 2-level tree, I can multiply it down and get and return a single constructor. And the delta here is this function, which I've tried to encircle here, assigning to every position a 2nd level of constructor. Okay, so
can I ask a quick question?
Yeah.
Is the previous structure basically an index W type, or a presentation of an index W type?
That's right. Yeah. So these things go by various different names, but yeah, it's just this particular setup is very common in type theory. It's the presentation of an inductive or co-inductive type is the way I think of it. Okay, but we have more. So we have a multiplication operation on elements of our universe.
Sorry, but it's an algebra of an index W type, right?
Right. It is. It's. I mean, what do you mean? So the monad actually can be written as a kind of algebra. Well, let me come back to that. So for now, this is just more structure. It has a function, a unit function, and a multiplicative function. And now for the somewhat drastic step is that I'm going to add computational behavior to these monads. I'm going to make them definitionally associative and unital. Here, yeah, big shout out to the Agda developers, because the rewrite rules are absolutely fantastic. In modern Agda, we can actually modify the definitional equality on the fly. And this is fantastic for prototyping new ideas about type theory. And so here, here's what the unit law says. I hope it can, I mean, I realize the code is pretty dense, but let's read through the first one. It says if I have an index and a constructor of that type, and I multiply C with the function which assigns to every position the unit constructor at that position, then I get C back. Right, exactly. So the elements of this universe, and similarly, there's a unit left law, which says that when I multiply over with the base being the unit constructor, it's the value of the unique position. And there's an associative law, which expands multiplications over multiplications into multiplications of a different decoration. Now, one thing that I'm glossing over a little bit here is that these monads need to be Cartesian. The multiplied constructor needs to have the same positions as the sum of the positions of the local constructor and the things glued to it. And you can implement that by having certain elimination principles for the positions, and these also need some rewrite rules. So I'm giving a vague overview. You'll have to consult the code to see how that works. But so there's more laws in order to get the Cartesianness, which is important for what we're doing. And so when you see these things like the position here and the position here, these are part of the structure that I'm eliding for the purposes of this talk. to simplify things. But as a first, but a reasonable approximation is to think of these things as monads, which are unital on both sides and associative, strictly.
So the maps2 symbol is just equality, or
no, the maps2 is Agda's symbol, is the symbol I'm using for the rewrite relation. So so to add a rewrite, I postulate an element of a relation, and then Agda reduces it. So this is so this orients the rewrite rules for this signature. And I have not proved anything like this, but I sort of claim vaguely that the signature of a polynomial monad is nicely normalizing in some sense. It's essentially just associating right and deleting units. Anyway, right. So because I've done this, this may seem a bit extreme. It is kind of extreme. This means that to be a monad in the universe is not something you can prove. It's not subject to be it's not subject to proof in type theory. This is not an internal type of monads for which you can create an instance. These particular monads are distinguished by the theory. But yeah, the point of this talk is to say that's okay, they're still useful. And so, right, so, but with this kind of thing in mind, that means that when we go to add something to the universe, we have to do it by hand. We're going to give certain, so as a first example, let's add a constant to our universe. The constant in this universe is the identity monad. Here is its definition. It has, its indices are the unit type, its constructors the unit type, positions the unit type, the typing function is trivial, the unit function is trivial, and the multiplication function is trivial. So, and for those, right, so as a polynomial in the categorical sense, it looks like this. And yeah, so I hope everyone kind of agrees. I mean, this is the annoying thing about this coherence problem is that this monad is surely definitionally associative and unital because there are, at least on closed terms, because there is only one closed term. So there's no debate about that. The coherence problem in type theory is related to the fact that we're usually obligated to prove things about open terms, and then we have problems because we have to use propositional equality. So here I'm eliding the proof that this is associative and unital and leaving that to the meta theory for us to sort of check. Of course, I'm not, you would need to check that with some kind of model theoretic argument, which I'm not going to give today, but yeah. Yeah.
Sorry, question is, what is the index I? Is that a pattern?
Sorry, yeah, just a note. I'm using so I have to use unit as an inductive type and not a record type here because of some issues with Agda's implementation of rewrite rules. So it's just to avoid name clashes in my library. So it stands for inductive. So the unit type as an inductive type instead of a record type. But that's a technical issue. Yeah, there are limits to what I can do with this kind of theory in Agda. I'm using Agda to sort of host the development of a new type theory, and there are limits to what you can do. And so you have to work around very delicately. And one hack here is that you need to use the inductive unit type. Anyway, okay. So we just added a constant to our universe. Now what we're going to do is we're going to add some generic constructors to our universe. So we're going to have a couple of ways of creating new monads from old ones. So this is just like you think the ordinary universe of type theory, it has type constructors. So if I have a type and a family over it, I can have a sigma type, or I can have a pi type, or I can have identity type. So I'm now going to close this universe of strict monads under a couple of constructions, which again are primitive to, if you like, the type theory I'm implementing. They're not definitions, they're primitive parts of the type theory. So the first one is that we can, given a monad, it's possible, and a family over its indices, we can, what I'm going to call re-index along this family, which is we can add a bunch of new indices in the family given by X. And yeah, by the way, I should say throughout, I'm writing the definitions as if they were definitions. But that's just syntactic sugar. They're actually being written as rewrite rules because this whole theory is being constructed as a type theory extending the definitional equalities. So I'm writing them here because writing everything in this form gets really, really ugly. So so these are, I'm writing them as definitions, but they're primitive rules. Okay, and the constructor of this re-indexed thing is just a constructor of the old thing and a function decorating all of its positions with the colors coming from our new family X. The positions are just the original positions. And the typing function given a pair of a constructor and a function, I have to give you its, and a position, I have to give you its type, or its index, and its index is supposed to be a pair of an index and an element of X. So I just look at the type of that position in the original monad and I apply my decoration, which I'm calling new, to P, and that gives me an element of X. So, so if you like the categorical interpretation of these polynomial monads, the category or even the double category of polynomial monads is a framed bicategory, and this construction is the framing. And the unit is given just by the unit of m and the constant function, and the multiplication is given by the multiplication in the original monad and composing the colorings, forgetting intermediate colorings or indexings. And here again, we see a couple of these positions that I'm just ignoring. So anyway, I have to move on, but this is the construction of taking a monad and adding new indices to it. And then we come to the sort of most important construction. And yeah, I should say, I don't have a formal justification for why this is, again, associative, but I claim that it's being formed out of something which was assumed definitionally associative, and composition of functions, which in type theory is definitionally associative. So, so that's my kind of non-argument for why this should be okay. But anyway, let's keep going. Okay, so the second construction is what's called which I'm going to call the Bias-Dillon slice construction, which is this construction of passing from a monad to, I think a nice way to interpret it is the monad of its relations, is the way I would say it. Concretely, the way that gets implemented is as follows. So given an M, the indices of this new monad, which is the slice of M. Oh, I forgot to write the sort of analog of the formation rule. The formation rule says that when I have a new monad, the slice construction is just an endomorphism of the universe. So given any monad, it spits out a new monad. And the indices of the slice are just a pair of the index of the original and a constructor of the original. So we sum the indices and their constructors. And then the constructors are now this, you can think of them as trees in the signature given by the monad. So it's like taking the free monad, this data type here that defines the constructors in the slice is something like the free monad on my polynomial.
What are we slicing by?
Yeah, so the name I'm using comes from the fact that algebras for this monad are monads equipped with a map to your original monad, which means that this monad classifies the slice category. So that's where the name slice comes from. The algebras are this, yeah, the category of algebras for this monad are monads equipped with a map to your monad. That's where, yeah. Okay, so the constructors are roughly like the free, except for we index them over a pair of an index and a constructor of M. And in order to do that, I use the multiplication that already existed in M. So the free monad would normally just be indexed over the constructor, over the indices of your original polynomial. In this case, you only need a polynomial to define the free monad. But to make this indexing work, you need that monad to be, you need that polynomial to be a monad, because I need to return a. Okay, so I'm not going to go into a lot of detail about this construction. I think it's a great construction. I've worked with it for a while. A lot of you have probably seen me talk about it before. But yeah, this is the workhorse which does a kind of dimension shift. A nice way to think of it, I think, is that, again, higher structures should have the property that their relations are also a higher structure. And so you can think of this construction as saying that the universe of monads is closed under looking at the relations of a monad. That's the way I think of it. A kind of identity type for this type of structure in a vague sense. Okay, so our universe now has a constant, the identity, and two ways of creating new monads from old monads. And again, all of this is at the sort of meta level. I'm thinking of type theory as extended with these properties. So now, so you may think, right, so I'm interested, I started off talking about being interested in doing higher algebra, talking about weak structures. And then I immediately went and imposed a bunch of definitional laws to make them definitionally associative. And the reason is because now I'm going to use this universe to reflect back into type theory and give a definition of what weak structures are. And the way that goes as follows: we actually already have enough information to give a definition of what's called an homotopy type. And so we're going to use this universe. So an homotopy type is going to be associated, there's going to be to a particular monad. So every monad comes equipped with its own kind of homotopy type, which, if you like, is the shapes that monad determines for its own notion of coherence. That's the way I think of what the homotopy types are associated to a monad. And the definition goes as follows: an homotopy type, at first, you need to give me a family over the indices of M. And then you need to give me co-inductively an homotopy type over, and now I apply my two monadic constructors. I pull back M along the family you just handed to me, and then I slice it using the slice construction. And that gives me a new monad so this is a monad expression, if you like, just like sigma and pi create new types, slicing and pulling back create new monads. And then I ask for an homotopy type over that monad. And so what's going on here is that the indices of this monad have changed. In fact, we'll take a look at them on the next slide. And so at the next step, after one unfolding, you're going to have to give me a family over these more complicated indices. And then we're going to incorporate that family you gave by pulling back along it. And then you're going to have to give me a family over those more complicated indices. So yeah, so this is a co-inductive definition of the notion of homotopy type. Credit does not go to me. This is actually the definition given in Baez and Dolan's original paper. They give this definition. All I'm doing is adapting it to type theory and cheating by making the monads strict in this sense. But the useful thing to note, though, is that the strictness is confined here, if you like, to this index. The family we give is just an internal family, and it can be any type. Yeah, it says set here, but again, that's just a historical Agda. I just didn't change everything to type. I don't mean to imply that it needs to be a set. Okay, so that's the idea. So just to give a quick intuition. So this definition co-inductively unfolds to an infinite sequence of families. Let me unfold it twice so that we just get an intuition of what it's saying. So let me fix something at the base level. So I fix an M, and I fix a family over its indices. And then the second level will be a family fill, which is over the indices of, this time not M, but the slice of the pullback of M. So if I unfold what the indices in this monad are, they are a 4-tuple consisting of an index, an element over that index, a constructor. And remember, this new is generated by the pullback construction. It's a decoration of that constructor in elements using the family. Okay, and so what I claim you should think of this as, you can think of a picture down here. It's like you have a constructor. The constructor comes with the data of its indices here. They're just telling sort of what types are running along the wires here. You've given me a family over this index set I. and you've given me an output element, and you've given me a decoration of the inputs with elements of E. So the idea of an open-topic type is that it's trying to capture the notion of a weak algebra over this monad. So if you think of what we had, if this was sort of traditional ordinary mathematics, and we were talking about the algebras over a signature, we would look at a constructor or an operation or whatever you would call it. We would have a carrier set, a sorted set in this case, because it's multi-sorted signature. And then to every collection of constructor applied to elements of that set, we would get an output element. So here, what this definition is doing is it's asking for us an infinite family, and the fillers are going to represent evidence that these three elements multiply using the constructor C to this element E. Okay, does that make sense? So the open-topic type consists of an infinite sequence of families of evidence about things being multiplied to other things under the monad in question. Okay. So let's do some examples. So now now I'm just gonna look at what happens when we look at a particular open-topic type. And remember, open-topic types are parameterized by a choice of monads. So I'm gonna choose our constant, the identity type. So I'm just gonna fix X. And we're gonna start to probe a little bit what is contained in this open-topic type X. So the first thing I can do is I can apply elements to X, and then I get a family over the indices of the identity constructor. Well, the indices of the identity monad are just the unit type. And so I can apply that family at the element true, and I get a set, and I'm gonna call that the set of objects of X. And similarly, if I have two objects now of this set, I can extract the fillers from X, which is a new open-topic type, and then I can look at the elements of that filler. And then, in order to get a set, I need to give an element in the in this four tuple of data, which is an index in this slice thing. And it turns out to be pretty easy in this case. It's just four things. Two of them are trivial, and there's an X and a Y. And so this is the type of arrows between these two objects. If I have an object and a loop, so an arrow from X to X, it turns out there's a particular open-topic shape that represents null homotopies of that loops. And so you can extract that. It's a two-dimensional shape, so you have to extract the fillers twice and then look at the elements. And then you have to write an element of, this time, a much more complicated monad, but here's a particular element. So I've written here the sort of standard pacing diagram picture. It's a loop, and then we're looking at the type of fillers of this loop. And this is a kind of open-topic notation where this is how you would write a loop, and the top thing is blank. The elements of this set over here are the fillers of this space. Similarly, you can, given two parallel arrows between X and Y, there's a type of disk fillers. Here's the open-topic notation. Here's the graphical notation. Here's the term that you have to write in order to extract a disk. And just for good measure, here's a simplex. These type check in Agda. Agda will help you expand out your little shapes here. So this is the advantage of, so our monads, when I didn't write all the definitions, but when I define the slice monad, I write down what its multiplication and unit are, and similarly for the pullback and so on. And so these definitions are sort of not opaque. They compute to things, and so the type checker can check when you've written well-formed terms. The thing that
question, sorry, that was 2 slides ago. Are you still inside that anonymous module parameterized by X?
So
okay.
these are all given an open-topic type. These are types that I can extract from an open-topic type over the identity. I can extract a type of null homotopies given any arrow. I can extract a disk given any 2 parallel arrows. I can extract a simplex given 2 composable arrows and a third, and so on. Okay. And again, the coherence problem is that this definition would never be complete. You never get out of completing this definition in an arbitrarily a non-truncated type, because to define things like to write the definition of how the slice monad computes, you'll need to use the laws. So by removing the need to prove the laws, I end up being able to write the function. And so I'm just considering that to be a primitive of this theory. Yeah, we can discuss later. People may want to know if that's justified or not, and we'll have to discuss it. Okay, so let me give a definition of now. So an open-topic type is just a huge number of families. It's just an infinite number of families which you can stick various shapes into and get types of fillers and so on. So now the question somehow is now, now that I've done all this, can we do anything with these objects? Can we actually prove theorems about them? Can we use them to prove interesting things? So in order to do that, I need to make some definitions. So let me say, I'm going to make the definition of having a unique action, which only involves 2 levels. It looks at 2 adjacent levels of your open-topic type, and it says, for every index, and well, it's written right here, a certain type is contractible. The type of outputs and fillers is contractible. I'll draw a picture on the next slide, so don't worry if this doesn't immediately become clear. And then I'm going to say an open-topic type is fibrant if it has a unique action at the first level, and if its filling type is fibrant. So this just says, this asks for this condition about a certain collected space being contractible infinitely often. Just follows the structure of co-inductively of open-topic type. Now, what is this condition? It's related to the data we saw in the previously, which is that you have this time you have your constructor with its type, with its indice information, and you're given the mu. And the open-topic type is fibrant if given just this data, the collection of e's on the output side together with the fillers is contractible. So this is the homotopy theoretic, a nice way to say there is a unique up to homotopy composite in this situation. So the extra data is witnessing all of the higher equalities that should exist in an algebra over this particular monad. So that's why I say here, a fibrant open-topic type should be thought of as kind of an implementation, internalization of the notion of a weak algebra over M. Okay. And so we can now go around making some cavalier definitions. Like we can say that an infinity groupoid is a fibrant open-topic type over the identity monad. In other words, an infinity groupoid is a weak algebra for the identity functor, which I think is a kind of nice definition of infinity groupoid. Similarly, an infinity category is an open-topic type, again over the identity, but this time you don't ask for fibrancy in the lowest dimension, which actually gives you invertibility. You just ask for fibrancy after skipping a single dimension. You can do other things, which is you can slice first. So if I slice the identity monad once, the Bias-Dolan slice construction generates the monad for monoids. And so an open-topic type, which is fibrant over the monad for monoids, I'll call an A infinity space. If I slice it twice, this construction gives the monad for planar operads. And so an open-topic type, which is fibrant over the double slice of the identity, I'll call an infinity planar operad. Okay. So, right, again, these are pretty cavalier definitions. We'd like to justify them somehow. So to give a first baby justification, I'm going to do the following. Opentopes and open-topic types generalize globular types. So if you recall, so let me just recall very quickly the definition of a globular type, which is that a globular type has a nice co-inductive definition. It's a set, and for every 2 elements of that set, co-inductively a globular type. Essentially the formation rule for the identity type in type theory says that every type is a globular type. So I'm going to call the globular type associated to X by its identity types. I'm going to call that IDG, the ID globular type associated to X. And let me have one more definition here. I want to speak about an equivalence of globular types. So same trick, we're going to use co-induction to say that an equivalence of globular types is, well, it's an equivalence of their objects. And then for every 2 elements, an equivalence between a globular equivalence co-inductively between their Halm globular types, okay? So there's a construction, as I said, globular types are a kind of a subset of opotopic types. So you can write a function giving, taking an opotopic type over a monad M and spitting out a globular type. This works for any monad, but you need to choose a particular index. So this works for every index of the monad. You get a globular type, and that's actually crucial for this to work. But yeah, and the definition is simple. So we at the base type, we take the elements, and then what we do is we use the unit of our monad in each dimension, which generates just these unary operations, and that extracts out a globular type. So there's a map like this. And the theorem is that if X is a fibrant opotopic type, then the globular type that I get by extracting it from this opotopic type is equivalent to the identity globular type on the space of elements. In other words, it's completely determined by the underlying groupoid. So, so this is a first sanity check somehow that that the notion of fibrant is sort of being well behaved or giving us something that we want, which is that we can prove, or I can prove that when you extract a globular type from an opotopic type, it's completely determined by the base space. What goes into this proof? It's actually not hard at all. It's just the fundamental theorem of homotopy type theory, which is Egbert's name, which I like is the name for the statement that whenever you have a sigma type is contractible, it can be interpreted as an identity type. And our definition of vibrancy was in terms of a particular sigma type. And this lets you create an equivalence with a given identity type, and then you can iterate this infinitely often and you get your globular equivalence. So this is not super hard. Okay. So this is, I consider this a first sanity check that we haven't done something completely crazy. On the other hand, this doesn't show that somehow my set of axioms doesn't imply UIP, so all of the higher ones are contractible or something like this. So it's not a rock solid thing, but I think it's nonetheless, it shows that at least this setup can let you prove some theorems. So to go further, we need to add a little bit more. And what I'm going to add more is I'm going to add not just the universe of monads, but we actually need monads fibered over other monads. So we need dependent monads. And so for the semantically minded, what I'm talking about is just a map of Cartesian polynomial monads, a Cartesian map of these monads. Unfolding that into type theory language, this just becomes a polynomial over a polynomial. I realize this can look intimidating, but it's really just boilerplate. If you unfold the definitions of this ladder of types into fibers, you'll end up with what I wrote right here. So anyway, so we're going to have a kind of second universe, which to every monad associates the notion of a monad dependent on that monad. And dependent monads have multiplication, and the multiplication follows the multiplication in the base. So this is a fiber-wise way of saying that this projection map, if I sort of take total spaces, is a homomorphism. So so it preserves actually sort of definitionally when I write it this way the underlying multiplication. So I can say more about that later, but I'm running a little bit out of time, so I'm gonna have to speed through a little bit at the end. So as an example, is the relative identity monad, the identity monad of the slice category sliced over a type A. But I want to define that as a dependent monad over the identity monad in the base. And if I do it this way, then the constructor, the indices are just A, that's the only thing that's sort of non-trivial. And then the constructors are just the unit type, and then multiplication and unit are also trivial. The constructors for our two constructors of the pulling back, reindexing along a map, and slicing also extend to dependent things. You just need to unfold, and everything sort of follows structurally what happened in the base. Maybe the only thing interesting to note is that when you pull back over, I just want to note this, when you, the pullback over, the argument you need is a family which is indexed by three things: an index in the base, an index over, which is associated to the monad. Remember, the monad comes with an extension of indices, as well as it should also, the extra thing you're pulling back over is also dependent on the thing you were pulling back originally in the base over. So I'll point that out. I use that for the next slide. Okay. So yeah, so I hope this is not too, yeah, it's notationally heavy, but I think conceptually simple. And the usefulness of this is that from a dependent monad, you can extract an opentopic type over the base. And how do you do that? Well, the elements are going to be, maybe not surprisingly, the just the indices of the monad you had, because they're already a fibration over the base. The dependent indices are fibration over the base indices. And then I have to have a monad over the slice of the pullback along those indices. And so I'm going to use the slice over and the pullback over and the indices over. And then I need to give this family Y. But here, the thing that I'm pulling back over in the base is the indices themselves. So X in this definition is indices over M. So it gets duplicated. And therefore, I can pull back over the equality of indices. So that gives me a canonical thing to pull back over. Right, so if I have a monad over, roughly what I'm saying is that these constructors that are compatible with dependent families, and because of that, I can extract, using the identity type, an opentopic type for any monad over. In particular, since the identity monad, I'm viewing it over the trivial monad, the identity in the base, this associates to any type an opentopic type. And you can see that the opentopic type is somehow incorporating more and more identity types of the indices. So that's, in this case, the indexes over will actually be A themselves.
Can I just quickly ask, so opentopic types over the identity monad basically are your definition of infinity groupoid, right?
Fibrant ones, not
ones.
Right? So the opentopic type is the raw data. The fibrancy is the fact that it has algebraic structure. So exactly, so that's where I'm going with this. So the next question is, can we prove this is fibrant? And the answer is yes, maybe somewhat surprisingly. For that, I have to introduce the notion very quickly. This last part, I'm sorry if it's a little bit speeded, of an algebraic extension. So, right, so you may, let's go back here. So my monads over are just, you can think of it as a monad equipped with a map over a monad. But said in a dependent way instead of said as a homomorphism. So you may know that many structures, many operatic type structures, you can often encode the notion of being an algebra as being a discrete fibration over the base. So, that this definition of being algebraic says is a predicate on a monad over. So if I have a monad and a monad over it, I can define what it means for that monad to, if you like, arise from an algebra, and it's that a certain collection, a certain space is contractible. And you may notice that this space being contractible for an algebraic thing is very much related to our definition of fibrancy, and that's of course not an accident. That's being done on purpose. Okay, so, but, right. So I'm going to call an extension, a dependent monad algebraic when it satisfies this, this condition right here, which roughly is saying it's something like a discrete fibration, or maybe a discrete op fibration. Okay, and so the main theorem is that if I have a monad M and a monad over it, and I slice it once using the definition that I just said, that this resulting extension is always algebraic. let me, yeah, so I think I'm running out of time. So, so this is the this is the work. So this is the part which is somewhat non-trivial. I'm gonna take it for granted right now. And you can ask me about the details maybe in the questions. Right, so after one slice, every extension is algebraic. And the corollary is that this produces a map not to opotopic types, but to my definition of infinity groupoids. Because it's easily checked that the identity monad that I defined is algebraic. And the notion of algebricity is cooked up so that it means exactly that the first level of your opotopic type is fibrant. And the theorem that the slice is always fibrant means that I can iterate that statement infinitely often. And so that's the construction of a map from set, which really should be called type here, sorry, this is an Agda thing, to my definition of infinity groupoid. And you can do a little bit better using the baby theorem that I said. You can actually show that when you get out, what you get out on the other side is the identity. If I extract the globular piece, I get back the identity types of A. So I didn't do something crazy to this thing. And of course, the natural conjecture from this point is that this map is an equivalence. And actually, if you go from one way is definitionally equivalence by the way I've set everything up. So it's really just the statement that the fibrant opotopic structure on a type is itself unique. That's missing. I suspect that can be done with the tools that have been presented here today. I think it needs a little bit of work. I frankly just ran out of time. But that's all I had. So I think I'll stop there.
All right, thank you very much. So we're now gonna thank Eric, and we're doing silent applause. So please don't unmute your microphone. We're just doing the video thing. And if you feel like by unmuting your microphone you're helping, you're not. Okay, so let's thank Eric for this great talk. All right, and now I'll open the floor for questions and comments and other things. And I see Thorsten is interested in asking questions. So yeah, feel free to just unmute your microphone and ask the question.
Hi, Eric, I have a question.
Sure.
It's a somewhat technical question about the Agda development. So it's very cool to see your strong use of co-inductive record types to do all this.
Yeah.
So a couple of years ago, I played around with trying to get familiar with globular sets by doing that, and I rapidly found that to prove things, I had to persuade Agda's termination checker by using size types. Do you have to do the same?
Yes. So this theorem here, I should have put an asterisk because Agda doesn't think it terminates, but I think it terminates. And I didn't go to the trouble of proving it using some auxiliary mechanism. But.
Yeah, I mean the size type seems to work quite well. I mean, yeah.
Frankly, I mean, I should get around to doing that. I haven't gotten around to doing it yet. But that is one problem. A second problem is, I see Thorsten is shaking his head. A second problem is that my definition of opotopic type, sorry, where is it? It uses a parameter, and this means that sometimes when the parameter changes, I think Thorsten wrote an email about this to the list not long ago. You end up changing the parameter in a co-inductive type, and this is a little bit annoying. It would be a little bit nicer if this was a sort of dependent with record type where I could put this on the other side and I had destructors or something like this. So there are some things about the setup right now which are not completely ideal. And yeah, but again, as I say, this is attempting to host what really I think should be thought of as kind of an independent extension of type theory.
Great. We have 3 hands raised, and I'm going to say, don't raise your hand, just go for it. It's pure unchecked capitalism, no socialism questions.
Yeah, I tried to raise my hand, but then Andy was in first. That doesn't matter.
Exactly, my point exactly.
Yeah, who cares about raising hands?
No discipline. So I think this is really cool stuff. And as somebody else already mentioned on the chat, luckily there is a video and I can replay it in a slow motion and then maybe understand a bit more. But that's cool.
Yeah, sorry, I knew I was going to have to go
criticism.
faster,
Was not a criticism, but here's a comment about the type theory rather, because I think you went really trigger happy with postulates and rewriting rules, which is in a way okay if you want to do things quick and dirty, but let me tell you that you don't need to be dirty at least, yeah. Because and sorry, this is meaning you need to. I mean, in a two-level theory, you can avoid the postulates you made because you can define these monads which have vibrant, in the sense of type theory, aspects in the strict setting, and then you can prove all these theorems, which is conveniently postulated. And fingers crossed, yeah, I'm sure it's right, but maybe it would be nicer if it would be actually verified, and you still can have yeah.
Absolutely. I mean, I agree with that. Yeah.
Yeah, you can still have the rewriting rules, but basically what you do is you have an equation you can prove, a strict equation, and then you say, okay, I now want to use as a rewriting rule, which is nothing else than sort of localized extensional type theory. Yeah. So what I'm saying is, I think in the two-level type theory, which you thought is not the right thing, but actually I think it is. You can do everything you were doing, but minus all the postulates.
Right. Agreed. In some sense, I agree that I'm attempting to be a minimalist here, which is asking sort of what's the minimal extension of type theory I can do so that we can talk about coherent structures.
But sorry, you're maximalist because you have lots of extensions which are not necessary. There is one extension which I think is necessary, because when you define this notion of an opotopic type, this was just on the slides, this co-inductive definition, which is indexed over these monads, which in my world would be a strict type and not a vibrant type. Then the question is, why can I take a co-inductive type indexed by a strict type? But and I had the same situation, and I believe that this is equivalent to just saying that the strict natural numbers are co-vibrant, which I think is a very minimalistic extension of type theory. But
I agree. I think for meta-theory, you're absolutely right. I'm attempting to have a version of type theory where everything is just the identity type, where all types are vibrant.
I think that's not a good idea, but okay, let's not.
It's a personal position. Yeah.
I know.
Can you hear me?
Yes.
Yeah. First, thanks. This was a great talk, and it has helped me to understand what you're doing. Yeah. So I'm also looking forward to having this on YouTube. So now my question is about understanding where your proposal is positioned compared to two-level type theory and synthetic extensions, like you had something on your first slide. And so I'm thinking, well, now I'm going to contradict Thorsten in some way, I guess. So one use case of two-level type theory is you use the outer strict layer to formulate axioms, which basically adds something to the vibrant theory, right? The vibrant theory is what you're ultimately interested in, but you can use the strict layer to formulate some axiom which says, for example, that, like what Thorsten said, NAT is co-vibrant, or you have some way to talk about some vibrant classifier for semi-circular types or something like this. And now after you've done this, we would like to have some way to hide the strict setting from the user in some sense, because as you said, we want the user to only have access to vibrant or homotopy invariant types. But in general, we don't really know how to do this. But it seems that your proposal basically gives one way of doing this for a very for one specific
right. So that I think
set of axioms.
I think that's a reasonable way of interpreting it. For me, there's a sort of a sort of philosophical component to what's happening here, which is that my opinion is something, or I've come to sort of think that what's happening here is that we have this experience from set theory that all structured sets can be defined in terms of sets. And there seems to be a kind of fundamental obstruction to that picture, that everything is reducible to homotopy types. Structured homotopy types can be reduced to homotopy types. And so my sort of attitude is, what that says is that the notion of structured homotopy type needs to be defined at the same time as the notion of homotopy type. And so that's what this is an attempt to do. This is an attempt to give sort of a parallel universe of structured types at the same time as types, but to search for a set of axioms that make that class of structures closed under reasonable operations, but without having to say that they're presented by set theoretic objects. Does that make sense? I don't know if that's a...
Yes.
Yeah.
Right. And also, I was wondering, I mean, I maybe this is partially just a personal preference, but like my favorite model of infinity categories goes via the simplicial route. So I was wondering whether you have a specific reason for choosing this extension. I mean, you could also, well, I don't know, but I guess you could also have created some extension which has well, a more minimalistic thing built in.
Okay, so right. So actually, that leads me to ask a question, because I don't know. I've been wanting to pose this as someone who's thought a lot about simplicial types. Here I've sort of presented a sort of finite list, if you like, of definitional inequalities that, if added to type theory, sort of seem to allow us to get a definition of the kind we want. Is there something similar for simplicial types? I actually don't know. I'd be curious to know. But to answer your more general question, the reason I prefer this approach for type theory is twofold. One, because these opentopic types are created out of the very kinds of definitions we use, inductive and co-inductive definitions in type theory. So I've always thought that they should somehow be well suited to defining coherent types and coherent structures. They're sort of based on the same kinds of things that we use to define. I mean, types in type theory, when we take initial algebras and terminal coalgebras, they are being defined as algebraic structures and algebraic structures of the kind I'm discussing here today. So it seems to me that it's always seemed to me that this should be not just a coincidence, that this should make this approach better. The second reason is that so simplices are fantastic for describing associative structures. They're extremely well suited to that. But if you want HOT to be a language of all higher structures, you need something much more general. And these opentopic types, they're somehow the version of higher structures that are built out of syntax for me. That's what I think of this as. And I think of the monads that I've strictified as being exactly those that I need to write higher dimensional syntax. So I think of this as the syntactic approach to higher structures, which is why I sort of prefer it for type theory. That's
yeah, that sounds
okay.
Yeah.
Sorry. So in the interest of time, I'll allow only short questions, not long pre-prepared statements. So if you have a short question, please ask it. But if you'd like to make a long statement, maybe this can wait with the posting to the mailing list.
I have a short question. What about infinity 2 categories or infinity n?
Right. So I think the setup here is sufficient to mimic Baez and Dola's original definition. So you would posit that it's fibrant after, for infinity 2 categories, fibrant after 2 dimensions, and that in dimension 1 you have enough universal cells in their sense. I haven't worked out how that goes yet, but I think something like that should be possible.
Hi, great talk, thanks. Can you hear me?
Yeah, yeah.
Yeah, cool. Couple of really short questions. So if you include fibrant homotopic types into homotopic types, this should have a left adjoint, right? That's a localization.
Yes, right. So exactly.
Do you have a way of constructing that as a function?
I would love to look at that because that goes to what Nikolai was saying actually, is that when I say this is the syntactic approach, somehow that left adjoint should itself be just constructed by giving the language of what it means to be fibrant. And whether that can be written down, I haven't gotten far enough to check, but yeah.
Okay, and the second question is, your final conjecture should have an external version, maybe that looks something like functor from simplicial sets to homotopic spaces, however you encode them, simplicial presheaves and homotops or something. That's an equivalence, equivalent equivalence, right?
Maybe, except for there's not necessarily. Oh, okay. If you want to work with a particular model.
Yeah. So you just
like the simplicial model of type theory, then yeah, I think you would get some kind of statement along those lines. Yeah.
Okay. Yeah. Okay. So you don't know if something like that is.
I don't know. I don't know.
All right. Final quick question. Just one in the chat. What about the theorems for the other category-like things? I know if we addressed that. If I missed it.
Yeah. There are no other theorems yet. You will notice if you go on the GitHub page that I committed this last theorem 15 minutes ago. No, I was just kidding. I finished it last night. So yeah. So this is.
Wait, really? 15 minutes ago? In the middle of the talk?
Okay, sorry. 15 minutes before the talk. Sorry.
Okay. I think in the interest of time and giving everyone a little break, I'm just going to say let's thank Eric again for this great talk. So please join me in applause. Okay, and that's it for the first talk. Folks, we'll be right back after these messages from our sponsors.